So I will talk about deep learning and remote sensing for ecosystem monitoring. So what we do is that we combine remote sensing, think satellite imagery, radar imagery, with machine learning and some physical mechanistic models for making predictions about ecosystem properties. In this talk, I will give you some examples of that, particularly where we use deep learning for segmentation objects in satellite imagery or aerial imagery. And then I will talk a little bit about fitting and uncertainty quantification of allometric models. So these are extremely simple mechanistic models. And then I will talk about bias correction when using deep learning for regression to get rid of systematic errors, which is important if you integrate predictions over large area. So I hope that even if you don't work with remote sensing images, there are some very small technical details in this talk which I hope can be of general interest, and because they're all very simple, it's hopefully something you could directly implement in your work if it's related to it. So this is what I have planned today. So who of you have been at the Nordic AI Meet in Oslo? Okay, not so many. So you can now answer emails and come back at, so for the first two, they will sound familiar to you, but I need them to set the stage. So I will talk a little bit about segmentation using fully convolutional neural networks. Then we'll talk about tree counting. And then the rather new stuff starts here with biomass estimation from the tree crowns, and then biomass estimation from LiDAR point clouds of trees again. And then, if time permits, I will talk a little bit about a new project I'm excited about, where we use machine learning and remote sensing to make a risk assessment for vector-borne diseases like malaria. So, just two slides, general on segmentation from the program, and actually what I accidentally overheard in the bus, there are a lot of people here who work actually with semantic segmentation and deep learning. So segmentation is a task where you have an input, typically an image, but it could also be a time series. It could also be, or in this case, this is a 2D image. It could be a 3D image. And the task is not to classify the whole image in being a cat or a dog or whatsoever, but to basically assign each pixel in the XY domain, in this case, to a particular class. So in this example here, you have the input, which is, in this case, a satellite image, and then the output, every pixel would now be assigned to whether it belongs to a tree or not. In medical image analysis, this could be an MRI scan, and then you would like to segment healthy versus diseased tissue on the label of the individual voxels or pixels. Okay? So, and throughout this talk, I will basically use the well-known UNet architecture for semantic segmentation. So this was proposed by Ronneberger and co-workers at MICAI. So as you heard in the plenary yesterday, there are many good ideas from medical data analysis which have had a broader impact in other fields, and this is clearly one. So it was proposed for medical image segmentation, but I would say it has become one of the go-to methods for image segmentation across fields. It's an excellent paper. So while some modifications have been proposed to this architecture, basically people use it very closely to the original paper. I'm really impressed. They kind of nailed it. It's a really strong paper. So this network architecture, which is depicted here, it's called a UNet because if you depict it like this, then it looks like a U. Right? That's the reason. And very briefly, what it does, you have here the input, and then it's downsampled along this line. So these gray blocks here are convolutional layers. And then going down here, you have some downsampling operations like a max pooling or something. And then here you have an upsampling. You can also say this is an encoding, this is a decoding. You have some upsampling operations and convolutions so that you get back to the original size, because in the end you would like to assign a label again for every input pixel. What's important is that you also have these lateral connections here. So you concatenate the feature maps you produced from the downsampling path with the corresponding feature maps of the upsampling path where they have the corresponding dimensionality. Okay. So, and many modifications are used. Also, if you go to work we are doing, you could do some fancy stuff here if you like. You can, if you would like to use a pre-chained architecture, you can replace it by a ResNet or an efficient net or a ConfNext or whatsoever, some vision transformer if you like. And there are certain hacks you can do about it. Sometimes the one architecture works better, sometimes the other. So there are two things, if you stick to the standard architecture, which I actually like doing, there are two things I would like to recommend you should do. And these are very, very common tricks. Perhaps you all are already using that. So for the upsampling path, don't do up convolutions, but use something simpler. So I would suggest using the most simple method, which is called nearest neighbor upsampling, which is indicated here below. You just duplicate the pixels, right? So if you go from the lower dimension up, right? So you just, if you have if the 2 × 2 upsampling, so this single pixel becomes these 2 × 2 pixel in the next level, and then you apply the convolutions to that. You have much less artifacts compared to upsampling operations. No additional parameters, simple, works great. It's typically an improvement. And the other thing is that the original paper, but that's, I mean, that was just the time, 2016. It uses ReLUs. I mean, and if you're not in theoretical analysis and want your system to be piecewise linear, there's no reason to use ReLUs. You would like to have gradient information, meaningful gradient, exploitable gradient information over the whole input range of your transfer function. So replace it by something which gives you that. I use an ELU often, but you can use a leaky ReLU or whatsoever. So you don't want to have a flat function here. Just this change typically increases the performance of your unit. Okay, questions so far? So, if we have this in place, how can we use this for tree counting? So, and why are we interested in trees anyway? So, there are many initiatives currently who are reconsidering trees and forests, because we realized that they are very important ecosystems, and in particular they are in the focus now because they store carbon, right? So they are carbon sinks, right? And this then helps for climate change mitigation. Or the other way around, if you remove trees and forests, then if then the carbon stored in these plants is released to the atmosphere, then this has a negative contribution, a negative greenhouse gas emissions. There are a lot of initiatives to counterbalance this. It's explicit in the Paris Agreement. It's part of the Bonn Challenge. If you heard about this, there's initiatives like REDD+ for increasing the number of trees and in countries. Typically, the amount of forests and trees are monitored by so-called national forest inventories. However, as the name says, they focus on forests, not on individual trees. And as we will see later, thereby they miss a lot of trees. However, the methodology used to monitor the size of forests varies a lot conceptually, so starting by defining what actually a forest is and the quality of the methodology. So, therefore, we think it's of utmost importance to have an unbiased independent monitoring system for measuring how many trees and forests and how big the forests are. I mean, this clearly that this also has the importance of this will just grow, right? I mean, if you hear about, you heard perhaps keywords like tree credits or carbon credits, right? So if countries start to trade carbon credits, and you have initiatives where people say, oh, we planted a lot of trees here, then you kind of have to check up if this is really true, and if this was not compensated by cutting some trees and logging some trees somewhere else. It's widely acknowledged that all these carbon offset initiatives where you can buy, you get a bad conscience, right? So if you fly here and then you compensate by this by buying some kind of carbon offset somewhere, and it's one of the biggest criticisms there is that you cannot check the long-term things, whether they really planted new trees, or if some trees somewhere else disappeared, and so on. I think that's. I hope that this is clear. And there's a really big problem. Is this focus on forests and not of individual trees? So individual trees could be interesting both for farmers who put them on their farmland, and there are also stories where countries reported, look, we're doing very good. Our forest amount has been constant over the last years, but it was very, very well known that they cut really significant amount of non-forest trees. And again, so depending on what forest definition you use, it's very easy to define also non-forest trees, which you then can cut. So, sorry for the long introduction, just to give you motivation why we're doing that. When I will talk about that we detect a lot of trees outside forests, it's very important for me that I don't make a wrong impression here. So the loss of trees and forests is a really, really big issue. So if you just look at Africa, then in the years between 2010 and 2020, yearly, so every year, 3.9 million hectares of forest were lost. It's an insane area, right? So the deforestation and land degradation is a real issue. And it's one of the ways, actually, to, we not only have to stop this, we also have to reverse it, because we would like to bind the carbon that is emitted in new plant biomass. So we had initially a focus on non-forest trees. And they're important not only because they store carbon, but they're also important for biodiversity. They provide food, shelter, and so on. They're important for humans and animals for several reasons. Here you see actually an area in Africa, a rather dry area, where you would perhaps initially not expect that there are trees, but there are obviously many. And this is not a forest here, right? So these are all non-forest trees. So in the forest mapping, all those would not occur. So we wanted to apply deep learning for counting these trees, and we basically apply a unit as I showed in the beginning. So for this you need training data, and then my colleague Martin Brandt, he sat down and manually labeled 90,000 trees from 400 different training sites across West Africa, which you see here. And there was a focus on dry areas. So this goes from 0 to roughly 1,000 millimeter rainfall. So in the south, you have actually a couple of trees, but in the north, it's really, really dry. And then it eventually becomes a desert, Sahara, so you don't have any trees there. So we analyzed rather high-resolution satellite imagery. So in this study, the resolution was 0.5 meter. So this is really high-quality data. So, and this is nicely summarized in this video by my colleagues from NASA. This is our study area. And you see it covers different climate zones, as I mentioned, so characterized by different tree densities. And if you now zoom in to Senegal, this is how it then looks like in this area. Then you use the UNet to detect all these trees, and then you determine the corresponding polygons, and then you start counting. And obviously these are many, and this clearly that this has to be automized, so this cannot be done by humans. So in this very first study, we looked at this area where which covered 1.3 million square kilometers, and where we counted 1.8 billion trees plus. So, and we were actually surprised a little bit by the amount. Here you see in this image again how the tree density varies across the rainfall gradient, so depending on how much rain there is in this area. And then we verified these numbers by, as you would typically do as a machine learner, using some holdout validation data, but also having colleagues going, doing a field study in Africa and checking that this is also actually true. So that was my more general introduction. So, and now I would like to talk a little bit about what we're currently doing or what we have been doing in the last month. So the next step, once you have the trees, you would like to determine how much carbon they actually bind. And this we did for a full country, namely the country of Rwanda. Rwanda is not very big. However, it has very different landscapes and very different vegetations. It has these isolated trees, it has trees in urban areas, it has rainforest, it has a lot of plantations of eucalyptus trees and other things. So there are very different scenarios where you can find trees. So this is actually much more challenging than the task I showed you before. Particularly, we have to deal with forests, and that required the real extension of what we did before. So the procedure was that we first mapped the individual trees, and then applied an allometric equation, it's called, which maps from crown size to the corresponding biomass. And these allometric equations, they look like this. So, and we will talk about them in detail later. So here you see the different areas, much more variety here. And here you see a visualization where the trees are now colored according to our estimate of the biomass or the above ground biomass in the corresponding carbon they bind. So we can basically now talk or look at each individual tree and check what is how much carbon is it binding. And what we found actually for Rwanda is that almost 90% of the trees are actually outside natural forests. So that's of course remarkable, showing that just a natural forest inventory gives you a very incomplete picture. But although natural forests only cover 11% of the tree count, they actually bind 51% of the carbon. So this again highlights the importance of old conserved natural forests compared to newly planted trees. I mean, if you have newly planted trees, right? So they're rather small and young and don't bind much carbon, right? Because they have a small stem and are not very high. but it's also like if you have a real forest, it has several layers, several stories, right? So there's much more to gain from preserving the existing forests than planting new ones. This method works, although it was trained on data from Rwanda. So my colleague Maurice and co-workers, they again labeled roughly 90,000 trees again for just for Rwanda. And but we also tried it in other areas, like the neighboring countries, Uganda, Kenya, Tanzania. So and it also works there. Also for fun, we applied it in France and in Denmark. So the method is actually quite more general than we expected without much tuning. So what was then the next step? The next step was, of course, well, if you have a system that works on West Africa, could you not just extend it to the whole subcontinent by just going up to the east coast? And this is what we just did. And I'm happy to show that you're basically the first one to see this. This is coming out very soon. So we now have a system where you can go in to a database and check up on every tree of northern Africa, starting here, then going roughly to 1,000 millimeter rainfall area. So it doesn't cover forests up to now. And methods like this, you see how you then use this in a more applied ecological setting. Here you have two areas, and we can now see how the biomass changes over time. And this is a very nice example because here you see actually an increase in biomass from 2002 to 2021, which is here encoded by the lighter, the color in the square. That's the average carbon bound in that area. So, yes. Questions so far? Yes? Yes. So, yes.
Where did you get the images?
This depends on the study. So in the first study, these are images we bought from PlanetScope. So these are commercial images. And the Rwanda images, this is from the government of Rwanda. These are aerial images, so this is not a satellite. This is mounted to a plane and has a 25 centimeters resolution. And so we are in contact with the government of Rwanda, and they would now repeatedly use this to monitor their carbon stock. So therefore I'm happy about the Rwanda thing, because this is really where the policymakers are now using these techniques to check. But it's actually, of course, it's a little bit a pity that these data are not freely available. Yes, so you cannot, so you need a high resolution to get, because if you would like to capture small trees, obviously. That leads to, but this also leads to some things where you as a researcher are a little bit unhappy that you cannot share it with other people, and also that our viewers cannot show these data. So we project the data on freely available low resolution scans, which are then taken from a different time point. And then if you go into the viewer, you have sometimes obviously disappearing trees, which we labeled, or alignment things. And this is just due to we evaluate different satellite data than we use for visualization. So in this talk, these are the real data. But if you go to our viewer, then you will see the classifications projected on some freely available low-res data. Yeah?
Can you match individual trees between the two images?
Here? Yeah, I would. So I haven't done so, or no, I don't know if anyone, but it should be possible. In particular, if you would look like at images in the years between. Then you can, but here you can, I mean, you can inspect every image here. We have the exact location. The trees do not move, right? So therefore we could follow, we can follow each tree. Yes?
How do you know that your biomass estimate is accurate for ground truth?
Well, I know that it's not accurate. I will come about this yet too. So first of all, I will talk about this. This is now it gets a little bit technical. That's a very good question. So, I mean, these allometric equations are calibrated from invasive measurements of the biomass. So we know basically, we have kind of a database of a certain number of trees that were cut, and where we know the crown area, and then we know how much biomass was in the stem, how much biomass was in the roots, and how much biomass was in the leaves. So this data is used to establish mathematical relations like this, mapping to biomass from the input here is, for example, crown area. These are approximations. So if you just measure, if you were allowed to measure two things about a tree to determine how much biomass it stores, you would measure the height and the diameter of the stem, because most biomass is in the wood, okay, in the stem. So, and then you would perhaps like to know the species, and then perhaps on rank 4, you would perhaps then look at the crown size, right? So, but from the satellite imagery, we only have the crown size. So we don't directly have the height. Spoiler, we can of course combine this with data from the JEDI mission, which gives us height estimates. So this, well, that's ongoing stuff, right? So, but if you don't have height information, then it's clear that there's a big uncertainty, okay? Yes, so another question is, how can we quantify this uncertainty? And this is actually what this part of the talk is a little bit about, because that's a very big issue. So we want this work to influence what decision makers do. And then there's a very valid question, as always when you use machine learning in the sciences. So how good are your predictions? Can you put prediction intervals around the values? And for this, you have to do an uncertainty estimation. And that's actually rather easy for the tree counting. You just look at a certain area, have a validation data set, and check how accurately you count. So how many trees do you miss? How many trees do you invent? Do you get the size right? So this you can do with standard techniques. But as this is a very, very good question, how do you do this with a biomass? Because you cannot go into a certain area, make a prediction, and then chop down all the trees there and check whether the biomass was really corresponding to what you estimated. So again, so you have these databases where you have this for certain areas. And for example, in the Rwanda case, to be a little bit more precise, there we use different equations of that type depending on whether it's a rainforest or whether this is a single tree or an eucalyptus area, depending, we have so a little bit, we take the type of tree into account. But of course, best would be if you would know for each tree what species it is. Anyway, so these are the equations underlying it. So if you have several inputs, and it's a combination of those. And these, what computer scientists would just, is the power law, right? Okay, so, but they're these typical growth equations. And what we then do is, based on these measurements we have from trees, we determine these coefficients B and alpha. And this type of equations is used, for example, if going from, I don't know, from stem size to crown area, from crown area to stem size. And so all these things are typically used based on these type of equations. So this is when I said, so they're very simple. It's clear that it's a total oversimplification, right? So therefore, they're kind of wrong, right? So they are only, on average, true. And the errors around the predictions, it's also a little bit obvious that they have a dependency on X. So it's not independent additive Gaussian noise here, right? So, I mean, that's clear to see just from the fact that the biomass cannot be negative, this is obvious. And the noise is not symmetric and so on. So that's a little bit tricky. So as I said, we fit the model parameters to data. And now I would like to remind you, so what is then desired if we fit to data. We would like to have a good fit with respect to a certain performance criterion. Think of the root mean squared error. Right? And, but additionally, we want to have a low bias, a low mean error. So the word bias is very overloaded in science. So here, the bias I refer to as a systematic error, which accumulates if you integrate over a lot of predictions. So you can have a system which gives you actually very, very good estimates of a low mean squared error for each tree, how much biomass it represents. But if this predictor always overestimates, then this error of overestimation accumulates if I integrate over many, many trees. And you see, we are talking here millions of trees, billions of trees, 10 billions of trees if you go to the whole northern subcontinental scale. And there you don't want this, right? So it's very important that we have a rather unbiased estimate here. And then, again, very good comment, of course, we would like to have as tight uncertainty estimates as possible, because these predictions will be used for something, and then you have to have some confidence in what you predict. So what is the traditional way of fitting these equations is that you take the logarithm on both sides, you do a log-log transform, and it looks like this, and then you consider A and ln B, the logarithm of B, as two parameters, and then you do optimal least squares. So you basically do standard linear regression in the transformed log-log space. This you can solve analytically, and then you get, in that space, the optimal values in terms of the squared error. Does this make sense? Right? This is what's typically done. If you then assume that after taking the logarithm, your data is normally distributed, or you do something to achieve that, and you assume that it is independent of x, or do some corrections to ensure that, you can compute prediction intervals in this log-log space. Right? So if you have all the assumptions of linear regression are fulfilled, right? Like this is a true model, you have normally distributed errors around it, the variance of the error is constant, right? Then you can get prediction intervals and saying with this certainty, my predictions will lie in this area. This I've done here, so without any corrections, it's really naive, just taking the logarithm and do the linear prediction here. Here you see prediction intervals for, this is, I just took one data set I just had lying around, so this is the biomass stored just in the leaves of African dry area trees. And yeah, this looks actually pretty nice. So here you have the different, this would be the 95% confidence interval, would be the light shaded area here. But important to note, it's trivial, but I still would like to stress this because there's a misunderstanding. We don't really care about log carbon. Log carbon is a totally irrelevant quantity. We're interested in the real amount of carbon. So we have to project this back. You see a lot of these plots here in papers. So you have to project this back into the original space. And then it looks a little bit not so nice, right? Anymore. The prediction intervals you get, right? So, yes. I'm very unhappy with this approach, which, I mean, it's kind of state of the art, but it's, I think we can do better. It is, first, it's totally clear if you do optimal least squares in the transformed space, this gives you not the mean squared error solution in the original space, right? So it's a suboptimal solution for the root mean squared error on the non-transformed variables. As a machine learning guy, this already makes you very feel uncomfortable. And the next thing is that if you have a model that is unbiased in the log-log space, it's of course heavily biased in the original space. This is so bad, I mean, it depends a little bit on the data, so sometimes it's not, but this can be so bad that this has been realized very, very early on. So these are, as you see from the references, these are not super new insights. This is not iClear last month, so that's more like here. This was the first iClear. Therefore, people have come up with ideas to correct this bias. So these are mathematically well-founded, but I still would say heuristics to correct the predictions to get rid of this bias. They're very famous from being, for example, the Baskerville correction from the early 70s. This should then apply as a post-processing step. But still, they don't give you, for example, the optimal least squares fit in the not transformed space. And of course, all these assumptions, they need not be met. So my background is a little bit in statistical learning theory, and I would like to have guarantees which are rigorous in the sense that I can say with a probability of 1 minus delta, this will happen, right? Here you have certain assumptions which you would actually need to test, and then you would perhaps realize that they're not really fulfilled. So for example, that the noise is not the same for all inputs, that your error is surely not normally distributed even after the log-log transformation. You have a misspecified model and all this. So these model-based assumptions, which are a very classic statistical approach, this doesn't resonate with me because they are all results you get there. First of all, they are asymptotic results, but that's not the biggest problem. The big problem is that they assume that the assumptions you make are met. And I see no reason why you should assume that. Actually, I can give you many, many reasons why you cannot assume that. And then you put in some heuristics to correct that, and then you mess up everything, and you don't get any real rigorous mathematical strict bounds. So we have to do something else. It's always very easy to criticize stuff, but here's something where I think one can do better. As already pointed out in the late 60s, why not simply fit this model using gradient descent? Like, every one of you would think, okay, why should I do this transformation? I just code this model and then throw it into your favorite autodiff framework and then optimize it using gradient descent, and then I get an optimal fit. Yes, this is what I think should be done. This gives us then a good fit, but then of course where do you then get the prediction intervals from? Because we would like to have statistical guarantees for our predictions. And this was also mentioned yesterday in the excellent keynote in the morning, we can resort to some distribution-free uncertainty quantification methods. So who of you has heard about conformal prediction? Okay, so that's, for example, one way how you can get prediction intervals without having assumptions on your model and the error distribution. It comes with some other problems. Of course, nothing is free, but you have only very, very little assumptions on your data. And the only assumptions you typically have is that your data is exchangeable, which let's translate this to the data being IID. That's a big problem in geoscience. And already you can debate how strongly this assumption is violated. But this is also the basic assumption for all analysis, classical analysis of linear regression or something, right? So all the other methods also break down if this is not fulfilled. So, and there you get rigorous statistical guarantees. So for example, for the methods I will use now, on the next slide, which is called the Jackknife Plus. This has a guarantee 1 minus 2 alpha cover. So you can actually prove that in expectation, 1 minus 2 alpha, if alpha is your confidence interval of the points, will really end up in that tube. And that looks much better, right? So this is original space, so this is not transformed space. And here you see the prediction intervals produced by the Jackknife Plus. When I learned about these techniques, I was excited, and then I thought, oh, but how should I don't really have the time to code so much, so how can I implement it? It's super nice. There's a free software package which is called MAPI, and which provides a lot of methods like the Jackknife Plus and other conformal prediction methods, and then using this package, it then takes you, I don't know, very, very little time, from depending on your programming skills, between 15 minutes and a couple of hours to get this running. So it's much less time than it takes to understand how the methods work. So in the following hour, I would like to walk you through the algorithm. I would walk in detail, no, but you can read this up. So it's actually not so complicated, because this is really the full description of the Jackknife Plus. It's almost, when you read first about it, I think it's too good to be true. So, but you really have to think about it, the expectations and stuff like this. So, but it's not too complicated to understand. Okay, so this is, I personally think, looking forward, this is the way how you should do the uncertainty estimation. In our current work, we have resorted to the standard techniques, making estimates on holdout data sets and stuff like this. But I think there's a lot of room for improvement in the future. Talking about room for improvement, I just told you that just having the tree crown area is not sufficient to give you a really, really accurate estimate of the biomass of a tree. So what's nice to do instead is taking the full shape of the tree into account, which is provided, for example, by LiDAR laser measurements, right? So which gives you 3D point clouds of the environment. So, and when you analyze those, you can get, of course, much more precise estimates of the stored carbon. The good thing is that this is actually used by many natural forest inventories. So for the Norwegian one, the Danish one, right? So they have all LiDAR data. And then, so concretely we use Danish data, and they go in a very systematic schedule. They have certain plots in the Danish forests where they go in, and then in a non-invasive way, estimate for a certain circular plot the biomass in this area. And what we now do, we take these super accurate, as accurate as a non-invasive method could be, right? So we don't want to log it down and burn and the stuff, right? So, and then look at the corresponding point clouds, and then we regress directly from the point clouds to the biomass, the carbon, and so on. This is not something new. I mean, that's a typical procedure that people look at these point clouds. They then derive some statistical features like quantiles of the distribution along the z-axis and feed this into some kind of power regression model or a random forest to make predictions. So that's kind of the state of the art. And this approach typically also requires a digital elevation model, so a model of the height of the terrain. So we make it here more basic, actually. We don't use a terrain model. We directly take the point cloud and throw it into a point cloud neural network. There are several extensions of neural networks to point clouds. You see actually how these inputs look like from different perspectives. And you see different, it's actually rather heterogeneous how the forests also in Denmark look like So you have different tree shapes, and just give an idea about the input to the system. Right? And then we throw it into a neural network architecture like this. And if you work on point clouds, then there's a lot of point cloud neural networks have been proposed. Typically, the application is more semantic segmentation or classification, driven by the car industry, for example. So, but here we regress. So we took the standard models and just turned them into regressors. And these are the results. Bottom line here is that you outperform the classical approaches, both in terms of the mean squared error and also in terms of bias. Am I running out of time? Okay. Yeah. Yes, okay, I'm too talkative. Okay, and bottom line here, so in the end we use the so-called Minkowski neural network. That's actually, you take your standard convolution favorite neural network and just implement it on top of a library which supports sparse convolutions, and that's it. So it's actually not really a system which is fundamentally tuned towards the input data points being cloud sets. It's just clever sparse convolutions. And then you can use this actually to make a forest map of Denmark, for example. And we also have colleagues here in Norway who are applying it to the Norwegian forest. Okay. No, actually one method. This is because this is either, if you do regression using neural networks, this is either the most boring and trivial thing you heard in the last year or the most useful. So, because if we consider a general regressor, and this could be a neural network, which in the end has a form that the last, if you're a neural network guy, the last layer is just an affine linear layer. So it combines a feature from the other layers in a linear way plus an offset parameter. Right? So this is typical how you would do regression. But this could be a random forest or anything. So now consider just this parameter, the bias parameter of your last layer for the deep learning people. So, and let's refer to this single parameter as bias for the next slides. Very overloaded term. Then, if you train your neural network in a standard way, namely that you do mini batches and then either you stop when you have a good generalizing network as evaluated on some holdout data, or your compute budget is ended, then you take this solution and this is your solution. Then you cannot assume that your residuals vanish. That means the sum of errors you make on your training data set will not be zero, simply because you just do mini batch updates and your beta is kind of fluctuating. Does this make sense? Okay. So this here is, if you do linear regression on the full data set, this is always fulfilled. But if you do this with deep neural network, it isn't. Right? Why should it? Right? So you never do the optimal B on the whole training or validation data whatsoever. And this leads to systematic error, which can accumulate then. You can have a super small MSE, yoo-hoo, and then you just apply it over a large map, and then the error accumulates. The good thing is, this is easy to fix. You just do one, as a post-processing step, you do one pass over the data and ensure that the derivative of your error function with respect to B vanishes. It's trivial. It's just you see the equation. So you either run over your training data, your validation data, or both. And this has a very, very big effect. So here you see a problem of emission. This is just some standard benchmark data you can download, where you say the blue curve is a neural network with a very low MSA, but without this correction, where you see that the accumulated error increases, and the orange one, the lowest one, is when you correct for this bias parameter. And the shocking thing is, and this is the green one, is if you just would use linear regression, then you get a bad MSE, right, because it's underfitting, but the bias is actually very small by definition. So this can make a huge difference if your problem is of that type, that in the end it matters if you accumulate errors If it doesn't matter, then this also doesn't matter. Good, I have to keep this out. Sorry. Next time. Yes, so I would like to thank again the organizers for giving me the opportunity to present this work.